Kinetics, high level 1, rate expression. Consider this raw experimental data showing how the concentration of a reactant changes over time for a particular reaction. You can see that we have time on the x-axis and we have concentration over on the y-axis. And if you remember, the rate for these equals the slope or the gradient for concentration versus time graph. So if we consider the instantaneous rate at various concentrations or times, using the slope of the tangent lines at those points, we can see that we get de-slopification. The reaction over time is the rate is decreasing. The slope is becoming less slopey. At higher concentrations, the slope is at its greatest. At lower concentration, it is at its lowest. And so, as reaction concentration decreases, rate decreases. Okay, let's consider the same data transformed to show how the rate of reaction changes with reactant concentration. Got concentration on the x-axis, we've got rate on the y-axis, and you can see that as concentration increases, the rate increases, or as concentration decreases, the rate decreases. But why do we need to predict how concentration affects rate? Well, obviously sometimes we want some reactions to be extremely fast, like when we want to blow something up. And sometimes we want rate of reaction to be very slow, such as slow release tablets. The rate of reaction can be expressed as a function of the concentration of the reactants. Let's consider the simplified reaction A going to B. The rate, which being moles per decimeter cubed per centimeter cubed per centimeter, equals the rate constant multiplied by the concentration of A to the power of the order of reaction. Order of reaction. The order of reaction indicates the effect on the rate of an increase in a given reactant concentration. Let's have a look at these reactions here, which show rate versus concentration graphs. The first one, you can see that the rate remains the same, independent of the concentration of the reactant. If we use the equation of a graph, y equals mx plus b, we can see that throughout y just equals the y-intercept, or in this case b. So x is having no effect. So the rate equals the rate constant multiplied by the concentration of the reactant, but the concentration of the reactant is having no effect, so it must be to the power of 0 to make it 1. The reaction is 0 order. The concentration has no effect on the rate. In this one, let's just write the equation for the graph out again. We can see here that as the concentration increases, the rate's increasing. So this time, as x increases, y increases. And it does it so linearly. So the reaction is first order. There's a linear relationship between concentration and rate. Here, we've got y equals mx squared, because we've got the exponential increase in the line. So the concentration must be to the second power. The reaction is second order. There's an exponential relationship between concentration and rate. Another way to look at the meaning of order reactions, we're going to, this is another way to look at it. It might help you understand what's going on a bit better. For A going to B, for a 0 order reaction, we get a straight line graph, as we know, where the rate remains the same. It's independent of the concentration of the reactants. So if we had a concentration of 1, the rate of the reaction is just K. We have a concentration of 2. The rate of reaction would still be K, because 2 to the power of 0 is 1. 1 times K is K. And the same for 3. 3 to the power of 0 is 1. 1 times k is k. So rate equals k. And of course, even if it was a fraction, like we had a half, we had 0.5 moles per decimeter cubed, we're still going to get k, because anything to the power of 0 is 1. Second, number 2, we've got a first order reaction here, and we know that gives us a straight line graph, passes through 0, and a linear relationship. When x equals 1, 1 to the power of 1 is 1, 1 times k is k. 2 to the power of 1 is 2, 2 times k is 2k. You're getting the idea here. So 3 would give us 3k. And 0.5 to the power of 1 is 0.5, 0.5 times k is half k. So the rate would equal a half k. Okay, 3, we have here a second order reaction. And we know we get this exponential line in our graph. So what's going to happen? If you've got a concentration, 1 decimeter cubed, 1 moles per decimeter cubed, 1 squared is 1, so rate is going to be 1k. What if we were to double it? If we double it, then we'd have 2 squared, which gives us 4k. So you see we've doubled this, but this has been increased by, it's multiplied by 4. What if we were to triple it? Then 3 squared is 9k. So we get 9k. So we've tripled this, but this has gone up times 9. And if we were to half it, you can probably guess, put 0.5 in there, 0.5 squared is quarter. Okay. Can you press pause and just have a go at those 3 questions? Okay, let's go through them quickly. When the concentration of a reactant changes from 0.45 moles per decimeter cubed to 1.35, the rate increases from 0.32 to 2.88. What is the order of reaction with respect to the reactants? Well, let's have a think about this. 0.45 to 1.35 is, it's times 3, isn't it? But going from 0.32 to 2.88 is, it's times 9, isn't it? Yeah. And so we know, as we went before, it's 3 times, but the rate is 9 times. We know it's second order, don't we? Basically, you look at the concentration and you can just square it. Yeah? 3 squared will give you 9. M equals 2. When the concentration reactant is halved, the rate is reduced by a half. Okay, well we'll see straight away, if concentration is halved, the rate is halved, then we know they're proportional, directly proportional, and so M must equal 1. Okay, must be first order. Number 3, we've got, when the concentration reactant doubles, the time of reaction change goes from 8 to 2. So it's not halved, it reduces, it's 8 would go to 4 if it's halved, it goes to 2, so it's halved again. So let me have a think about this. You're going to have, this would be times 2, and we can just go back the other way, this is times 4. And so it must be second order, because the concentration would need to be squared to get the increase in rate. So M equals 2. Okay, obviously we won't always be dealing with just one reactant. Often, or ordinarily to be honest, there's more than one reactant. So let's consider the general equation for a reaction with 2 reactants. The rate in moles per decimeter cubed per second. We've got the rate constant there, which can be variable. We've got the orders of reaction with respect to A or B. And M plus N If you add those orders up, you get the overall order of the reaction. Let's consider rate laws with two reactants, A plus B going to C. You can see that the first order with respect to A and with respect to B, M equals 1, N equals 1. So overall, it will be a second order reaction because M plus N equals 2. If we have 1 to the power of 1 and 1 to the power of 1, together you have 1, and 1 times k is k. If you have 2 to the power of 1 multiplied by 1 to the power of 1, 2 times 1, 2k. 1 to the power of 1 times 2 to the power of 1, again 2k. 2 and 2, so if you have 2 to the power of 1 and 2 to the power of 1, you're going to have 4k, so the rate will be 4k. If you've got 3 and 1, 3 times 1, 3k, 1 and 3, 3k, and if you've got 3 and 3, it would go up to 9k. So if you triple the concentration of A, triple the concentration of B, because they're both first order, the rate would increase by 9 times. Okay, let's look here. We've got A plus B going to C, and you can see here that it's second order with respect to A and it's zero order with respect to B. So B, the change in concentration of B has no effect on the rate. Overall, it will be a second order reaction, just M plus N. So here we've got 1 squared multiplied by 1, it's going to give us k. 2 squared is 4 multiplied by 1, it's going to give us 4k. We've got 1 squared multiplied by 1, remember, because if you've got B isn't involved, it's actually B to the power of 0, isn't it? It's really this. Oop, it's gone a bit slow today. Process is too hot. And anything to the power of 0 is 1, so this would be 1. So it's going to be k, or 1k. If we've got 2 squared, and remember, these will always be 1 because it's to the power of 0. So 4 times 1, 4k. 3 squared is 9, times 1, 9. 1 squared times 1, still 1. And 3 squared is 9, and this is still 1, 9k. Consider the rate laws with two reactants, A and B, where we've got a second order with respect to A and first order with respect to B. So up here we'd have 1 squared multiplied by 1, so it's 1 times 1, rate would be 1k. What if we had 2 and 1? It's going to be 2 squared. So if we double it, 2 squared, and then this will just be the same, 1. So it's going to be 4 times 1. It's going to give us 4k. Here we've got 1 squared multiplied by 2 to the power of 1, which is just 2, gives us 2k. 2 squared 4 multiplied by 2 to the power of 1, which is 2, it's going to give us 8k. So if you doubled A and double B, the overall rate is times 8. If you triple A, we know that's going to be 3 squared, it's going to be 9 times 1, 9k. 1 squared is 1 times 3, it's going to give us 3k. And here we've got 3 squared is 9 times 3, which gives us 27. So if you triple the concentration of A and triple the concentration of B with this setup, with the second order and first order, you get an increase 27 times. The rate will be 27 times quicker. Okay, let's have a look at these questions. Can you press pause, just give a quick go? Okay, So we have question 1. When concentration of both A and B double, the rate of the reaction doubles. When the concentration of B only doubles, the rate of the reaction doubles. State the order of reaction with respect to A and B. So we know if B doubles, so let's put, it's going to be 2. We know if this doubles, then the rate doubles. So this must be the power of 1. Which means A must be to the power of 0. Yep. And that's right. M is to the power of 0, N is to the power of 1. When the concentration of both A and B doubles, the rate of the reaction increases by a factor of 8. So we're going to go up to 8 here. When the concentration of B only doubles, the rate of the reaction would only double. So they're proportional, aren't they? So B must be first order. So that was doubled. It'd be 1. And it says both are doubled there, doesn't it? So it's going to be 2. So what would we need to put here to get an answer of 8? Well, it would be 2 times 4 is 8. And 2 squared gives us 4, doesn't it? So 2 squared multiplied by 2 gives us 8. So it's going to be M equals 2, N equals 1. Yes, and I'm right. When the concentration of A triples and B is halved, the rate of the reaction changes from 5 to 22.5. State the general rate law for this reaction. Well, first of all, what do you need to multiply this by to get to this? It's going to be 4.5. So 4.5 there. So we've got 5 times 4.5 gives us 22.5. When the concentration of A triples, yoink, and when B is halved, let's have a think about this. I should probably have worked that before rather than doing it on the fly. To get a 4.5, well, 3 squared is 9, and 9 times 0.5 is 4.5. So this is going to be the power of 1, isn't it? Which 0.5 to the power of 1 is 0.5. 3 squared is 9, so 9 times 0.5 gives us 4.5. So we're going to have a M2, N equals 1. And it's not there, just give me a second. There we go. Yes. 2 and 1. Okay. For any given reaction, the value of K depends on the temperature. If we've got cyclopropane being converted to propene, the rate is first order with respect to cyclopropane. You can see here that the rate constant at 477 Kelvin is 0.00018, but when you boost it by 100 Kelvin, it goes up to 0.03. So the rate changes, or the value of K changes, depending on temperature. The units for the rate constant K depend on the overall order of the reaction. So the rate is always in moles per decimeter cubed per second. And we've got the concentration units in moles per decimeters cubed. For 0 order overall, you've got K equals rate units over concentrated units to the power of 0. So we've got moles per decimeter cubed per second over moles per decimeter cubed to the power of 0, which is the same as having it over 1. So the units are just moles per decimeter cubed seconds to the minus 1 for 0 order. For first order, we've got moles per decimeter cubed per second over moles per decimeter cubed. The moles per decimeter cubits just cancel out, leaving you seconds to the minus 1. For second order overall, we've got moles per decimeter cubed per second over moles per decimeter cubed squared. Let's expand that. So you've got it over moles squared decimeters to the minus 6. Cancel those out. You get mole to the minus 1, decimeters to the 3, power of 3, seconds to the minus 1. So what about third order? Well, the moles per decimeter cubed for concentration will be cubed, giving us moles cubed decimeter to the -9. Again, just cancel them out. It's going to give you moles to the -2 and decimeters to the 6 per second. Okay, method of initial rates. The initial rate is calculated using different initial reactant concentrations at a set temperature. The order of reaction and the rate constant can be determined. In this example, we've got N2O5 giving us nitrogen dioxide and oxygen. When the concentration of N2O5 changes from 0.4 moles per decimeter cubed to 0.8 at 25 degrees Celsius, the initial rate of reaction doubles. So we know the rate doubles. The concentration is 0.4 moles per decimeter cubed and the rate is 2.1 times 10 to the -4. So the general rate expression is going to be K concentration of N2O5 to the power of M. The order with respect to N2O5 is going to be 1 because we know when N2O5 the concentration doubles, the rate doubles. So it's first order. Then you can just plug in your numbers, rearrange the equation first of all. We know what rate is, it's given there. We know what the concentration is, it's given here. Just do the math to get your answer. Make sure you get your units right, settings to -1. And so the rate is 5.3 times 10 to the -4 per second. And we've got it showing there, this is with respect to N2O5 first order reaction. Example 2. The initial rate of reaction for series experiments was performed with varying initial concentrations of A and B. The data is shown below. Let's write down our rate equation. You can see here that B is fixed and only A changes. A is doubling. And in trials 2 and 3, we're keeping A, the concentration of A the same, and we're tripling B. So we can use trials in 1 and 2 to find M. And M would equal 2. The rate quadruples when A doubles. And 2, we can use trials 2 and 3 to find N. And N would equal 1 because the rate triples when B triples. Then you can find K by putting in the concentrations and putting in the powers up here. And we know the rate. And we use trial from the first one there. We've got rate here and there. We've got A and B concentrations, B, and we calculated the powers over here. Next, we've got example 3 here. Have a look at that. We've got BrO3 minus and HSO3 minus reacting, and you can see in the trials here, we kind of, in trial 1, let's have a look, 1 and 3 keeps HSO3 virtually the same, and trials 2 and 3 keeps BrO3 minus virtually the same. Okay, and we're going to use an alternate approach to finding the order. We've got the rate at a fixed temperature for each trial. Like before, choose 2 trials where the concentration of one reactant is fixed and the other changes, and set up a ratio as shown at the right hand and solve for the order. So we've got concentration of the reactant over concentration of the reactant in the 2 different trials, and you've got the rate over rate of the 2 different trials, and you've got the order at the top there. Use the trial with the higher concentration in the numerator. So for example, if we were going to do let's have a think. If you're going to do HSO3 minus here, you would use this one would be the numerator. It is larger than this one. So the trial with a higher concentration goes on the top. Okay, let's do this. We've got the BO3 from concentration of BrO3 minus from trial 1 over the concentration of BrO3 from trial 3. Put them above each other. You see the one with the large concentration has gone on top from trial 1. Put the 2 rates in, do the maths, you have M there, and then you can't calculate M, it gives us 1. Do the same for HSO3, just do the maths, plug in the concentrations from the table, plug in the rates from the table, rearrange it, to find N. Oh man, what is it? So we use 1 and 3 for the BrO3 minus. We use 2 and 3 for the HSO3 minus. And then we're going to find the rate constant and state the rate expression at 30 degrees. So rate equals K, concentration of BrO3 minus, concentration ratio of 3 minus to the power of 2, second order. Plug in what we know, the concentrations, rearrange it to find K, and make sure you get the right correct units. So the rate expression at 30 degrees would be 3.48 moles to the minus 2, decimeters to 6, seconds to the minus 1, and that's with BrO3 first order and HSO3 minus second order. You've got to know the difference in relationships between concentration versus time and rate versus concentration graphs. For zero order reactions, you get a straight descending line. As the concentration decreases over time. The slope is constant, so the rate is constant at any reactant concentration. We know that rate equals the rate constant because the concentration is power 0, so it's just 1. So we get a straight line. Rate remains the same regardless of reactant concentration. The concentration of the reactant has no effect. For first order reactions, the instantaneous rate, the slope of the tangent line, decreases as the reactant concentration decreases. So you've got to put the lines in there, that's straight. You see it's getting less and less slopey. The rate is decreasing. Rate equals K, 8 of 1. You get a straight line because there's a linear relationship between the reactant concentration and the rate. Second order reactions, the instantaneous rate, the slope of the tangent line decreases as the reactant concentration decreases. The concentration is squared, and there's an exponential relationship between the reactant concentration and the rate. Okay, half-life. This is another way to distinguish between zero, first and second order reactions. It's a bit squished, but if you just have a look over here, you've got concentration on the y-axis and you've got time on the x-axis. You've got concentration of 0.16 here, right, at this time. Then you've got a concentration of 0.8 here. So the concentration is halved from here to here. And you can see it took this amount of time, okay? To go from 0.8 down to 0.4, from here, 0.8 to 0.4, took this amount of time. This time here is obviously less. It's about half, in fact, of this time here. So the half-life is decreasing. Oops. Here we've got, again, 0.16 concentration of reactant being reduced to 0.8. So the time it takes for the concentration to halve is here is let me just count it up. 1, 2, 3, 4, 5, 6, about 6.5 seconds. And then for it to halve again, to go from 0.8 to 0.4 is again about 6.5. So half-life is constant. The time it takes for the concentration of the reactant to halve is the same throughout the reaction. In second order reactions, you can see again 0.16 concentration going to 0.8. It takes this amount of time, but then to go from 0.8 to 0.4 takes a lot longer. So the half-life is increasing. The time it takes for the concentration of reactants to halve increases in second order reactions. Okay, I'd like you now to fill those in, and that's the end of this presentation. Splendid.